Light-sculpted crystals. A new era for nanoscale optical engineering researchers have discovered a way to write intricate, microscopic patterns directly into a crystal using nothing more than ordinary light. This breakthrough, involving a specific semiconductor known as arsenic trisulfide, as 2s3, could fundamentally change how we manufacture optical components, moving away from expensive, heavy machinery toward light-driven, programmable materials. The science of writing, with light at the heart of this discovery, is a phenomenon called photorefractivity. In simple terms, when certain materials are exposed to light, their refractive index, the measure of how much they bend or slow down light changes. While many materials exhibit this effect, the arsenic trisulfide studied by the XBANCEO Emerging Technologies Research Center and Nobel laureate Prof. Konstantin Novoselov is exceptional. It demonstrates a light-induced change in its refractive index that is significantly larger than that of industry-standard materials like barium titanate, Ba-T03. Why this matters? In traditional manufacturing, creating nanoscale structures requires cleanroom lithography, slow, incredibly expensive process involving complex chemical and mechanical steps. This new method allows scientists to use standard continuous wave, CW, lasers to sculpt optical functions directly into the material, bypassing much of the traditional hardware required for high-tech manufacturing. Precision at the nanoscale. The precision achieved with this crystal is remarkable. To prove the material's capability, researchers used a standard laser to etch a microscopic portrait of Albert Einstein onto a thin flake of As2S3. The resolution was so fine that points were spaced as closely as 700 nanometers apart. In advanced tests, resolution reached approximately 50,000 dots per inch, 500 nanometers apart. Because the refractive index changes so drastically, these patterns remain highly visible and stable, acting as permanent optical fingerprints. Beyond refraction, physical expansion, the material does more than just bend light, it also physically reacts to it. When exposed to light, As2S3 can expand by up to 5%. This photoexpansion effect allows researchers to physically mold the surface of the crystal into shapes like microlenses. Optical gratings waveguides this dual capability. The ability to change both how light passes through the material and how the material itself is shaped as a game changer for the next generation of wearable technology. Future applications. From AR glasses to smart lenses, the ability to manipulate light and matter simultaneously opens several doors for future consumer and industrial technology. Augmented reality, AR. The material could be used to create wide field of view waveguides, essential for making AR glasses thinner and more immersive. Smart contact lenses. The high sensitivity of these Van der Waals crystals provides a foundation for integrating complex optical circuits into tiny, wearable formats. Security and anti-counterfeiting. The unique, nanoscale optical fingerprints created by light are nearly impossible to replicate, making them ideal for high-security authentication. Next-gen computing. This paves the way for photonic circuits, where information is processed via light rather than electricity, potentially leading to much faster and more energy-efficient devices. By identifying natural crystals with this level of sensitivity, we are effectively providing the essential building blocks for a new generation of technology that is driven entirely by light rather than electricity. Valentin Volkov, CTO at XBANCEO, conclusion: by harnessing the photorefractive and expansive properties of arsenic trisulfide, scientists have moved closer to a future where optical devices are not just manufactured, but programmed with light. This shift promises to make high-precision optical technology more accessible, scalable, and integrated into our daily lives through advanced wearables.